Alright, we should be back. Make sure this is going so if anybody does pop in for a quick question, we are ready. Okay. And alright, so we're going to finish looking at the last class that'll be covered on the midterm exam, just so I make sure I know exactly what learning objectives to tell students to focus on for their studying for the Thursday exam. And so we have a decent class on Tuesday. So let's get right into it. Last time we noticed that we were able to use the Henderson-Hasselbalch equation to figure out 4, 5, and 6 a little bit more accurately. And we at least saw learning objective 1 covered. So let's see how many more mechanisms we can get through, because almost everything is going to be mechanistic. I wonder if we'll get to 6. We'll see, but let's go ahead. And again, you're not going to hear the audio from the actual class recording, just in case student names are talked about. But I'll comment on it as we're going. And this is so key, right? This is the most important part of, you have to know how these are connected. How the pKa is connected to the acid and the base is connected to the acid. The base is the conjugate base of the acid. The acid is what's telling us what the pKa is. He's talking about lysine right now. This OH is deprotonated, he's saying first. The other two amines. Remember, this is zwitterionic. This one's also protonated as well at pH, body pH 7. Remind us, when the pKa equals the pH, this has to go to 0. Log of 1 is 0, base 10. Talking about the reductive amination we looked at last time, being able to go backwards and forwards. Protonating the N. Water comes in. Going backwards, all the way the other way. The steps are the same, arrows are just reversed. Again, how do you drive this reaction? You remove water. Nice, moving into learned objective 2. Again, I'm surprised we don't necessarily protonate it. Asking why don't I protonate the NH? Well, it doesn't help us. It sends us backwards. It does. So he's showing us the backwards reaction. Do we because yeah, great. There's a good mechanism here where we can deprotonate one of these protons, kicking in, kicking out to the product. How electrophilic are these? What is the sigma star of these things looking like versus the instead of thinking about this lone pair coming in forming the carbonyl, kicking this off. His argument for why this is not happening is that if you do the reverse reaction, you need 3 molecules. You would need a water coming in and having a source of protons, entropy-based argument. Again, let me just make another point that everybody says in a graduate level, or everybody starts to talk about in college chemistry, which is that mechanisms themselves are a way for chemists to explain to themselves how electrons are moving, explain to themselves how a mechanism is happening, but it's impossible to prove a mechanism. It's only possible to disprove other mechanisms. And so mechanisms themselves are not a science in terms of their measurable, proven mechanisms. You just eliminate enough other mechanisms by his argument of entropy, by other arguments, or through experimental data to say why one is the most likely mechanism that these things are going through. But remind ourselves, too, that lots of different ways molecules can get to these lower energy wells of material, or you take advantage of equilibrium, remove the water to push it from one direction to the other. All right, and remember previously we were able to remove the positive charge from the nitrogen when it was a primary amine by deprotonating it, but here that's not the case. Where's the H we're going to get rid of? There's your carbocation. Right, he's talking about pKa's, I think, again, is what he's going to bring this back to. pKa of an alpha imine, alpha carbon, alpha, what would you call that? Alpha aminial CH? Because we called it the carbonyl's alpha proton. But in this case, that's more acidic. The green one is. When he says not kinetic, thermodynamics. When not sterics, electronics. Which, I'm just going to really quickly, you won't hear this on the stream. Well, I guess I could. Let me put the audio back on.
Steric.
See, it's not sterics, right?
Steric. Steric.
If you believe Google. Let's see if it's proven here anywhere. Kind of. Closest is kind of that one. Do we even have an example of the other one? SP2 versus SP3, I think, is going to be one argument he's making. He's saying, what about it is thermodynamically stable? Where are the electrons? So now there is no choice anymore. Gosh, so cool. So finally, kind of back to chemistry we've seen before. You know, some students will be really uncomfortable with this, but if you can see that the N and the O, yes, they're different, but the chemistry we're doing is the same. We're making now, instead of an enolate, we're not making like an 8. There is no ion, which again is complicated vocabulary, but we are doing a similar thing where we have this double bond, we're attacking an alpha carbon, making an ene, and the cation in this case is being neutralized. He's asking what's the very first step if we go backwards. How do we go back the way we came? We have to think about what was the step that got us here. And so we deprotonated, right, this H over here. So now these electrons are going to come down, come off, and grab an H. So done with 2. Uh-oh. Did we not get sound on this one? Alright, I gotta check some things real quick. I just muted it. Oops, don't do that. Nope, wrong one, wrong one. Focus, focus, focus. We don't want that one, we want to delete this one. So again, not an aldehyde. Ooh, ooh, ooh. So now we're looking at number 3. Where did this H come from? The reductant. Finally, we get to see Strecker synthesis. So, good news is none of these are particular, or well, so far what we've seen, the first three are not particularly different. Difference between 1 and 2 was what is our proton that's most acidic that we end up taking off, whether it's the NH1 in a primary amine or the alpha CH of the imine. Well, yeah, I guess kind of an imine. So first, same step as before. Go to electrophile again. We need an equivalent. We need this type of nucleophile that he puts in parentheses. Nice. We're going to need some water eventually. Some acid. He's asking where did the nitrogen go? It just becomes ammonia again, right? It just becomes more ammonia. Just to show people again, this is what, I don't think he's going to show this mechanism, but this is basically what's happening. You have an acid, protonates the nitrogen, O attacks here, this thing opens back up to here, proton transfer again, making this positive. Once again, we attack again, new thing on this, protonate it again, attack again, comes in, and we form the carboxylic acid that we need as this leaves as ammonia. I think we're going to go, so this is the cool part, number 6. Problem with enantiomers, they're identical. You cannot separate enantiomers unless you have a chiral column. Then it's possible. That's really expensive, so can we find another way to do it? because he's kind of setting the scene for there are sometimes the wrong chirality on your molecule is poisonous. The wrong one interacts with your body the wrong way, being poisonous. So what do? So he's saying, I've got this racemate, I've got R and S. I want to get just R or just S. How do I do this? You need diastereomers. So you're going to go diastereomers you can separate. You can separate them on a column. You don't need a chiral column. And when I say column, I mean column chromatography. They move differently through silica. They interact differently with silica's polarity. But I don't see. I mean, I almost want to show. You almost want to see. Maybe you don't have to show the whole mechanism, but maybe show a little bit more clearly what they're trying to do here, because he doesn't. He doesn't quite do that. But he hits you with the main point. He technically doesn't finish. So do I take it out? I think we make it easier on students if we just take it out. And we won't even have to talk about it in class necessarily. But again, like not a particularly difficult. Well, for me, it's not particularly difficult because it's a very mechanism-based class. But he finishes the other 3 mechanisms, and he doesn't do a great job with number 5. Let me post this resource just to the Canvas really quickly, so that way, if students are unsure, they have it. And we'll go through here a second and edit this, and we'll just add this as a link. Since that's not a lecture, and then we're going to say not tested on midterm 2. Okay, that was a pretty wicked fast looking at that one. Not sure how helpful this necessarily office hour will be for students, but I guess it's a reminder, or not a reminder, but just a either you're going to, if you like mechanisms, midterm 2 is going to be fairly easier to study for, because let's kind of look back at the schedule for a second. Let's kind of do a review of everything. So we're going to be looking at classes 6, 7, 8, and 9, where these ones are the same. So we're not covering a ton because, well, we are covering a lot, but 6 and 7 are one class. 8 is a new class, and then 9 and 10 are, again, a combined class. So overall, our learning objectives are a mechanism, explaining a mechanism, a mechanism, a mechanism, a mechanism. Here, we do a little bit of macromolecule talk. We talk about entropy. We talk about hydrophobic. We talk about new DL, but it's not that different than what we knew before. We do have to think about some math, some Henderson-Hasselbalch. So this class is the one that's not mechanism, the most macromolecule class. And Henderson-Hasselbalch is pretty important here. And then we move to another mechanism class. So so like 2/3 of this test is kind of mechanism based. 1/3 of this class is actually real macro. I shouldn't say real. It is mostly macromolecule discussion. So we'll see on the midterm, quite a lot of mechanisms are more likely to be tested at some point than well. And let's pause for a second and remind ourselves too that in some ways we are also looking at a little bit of class 5, right? Class 5 is partially up for grabs on this exam, especially talking about LDA. And maybe that's something I want to make more clear in class, is that the bulky base, the LDA, it's a good base, but it's bulky. This is like, let's look at LDA for a second. Well, LDA chemistry is always better to write. Right, this base, because it has these isopropyl groups, it's a bulkier base, and so it doesn't attack carbonyls. It tends to attack the alpha protons, and it tends to attack the alpha proton that's the easiest to attack. Goes through the kinetic route, and typically it's run in really, really cold conditions. So this is an important kind of thing to remember. So in some ways, we want to be careful that part of class 5 kind of gets talked about in class 6. So let me make that reminder in here a second. And so let's just give some students some reminders on that. And all right, I'm gonna leave this be as I mean, it's a very quick stream. Like, this is a 37-minute stream, and I really didn't need to watch this entire video because for the most part, it is just mechanisms. The reverse mechanism is the same. If you're comfortable with mechanisms, this class 10 is not that particularly difficult. The class that technically the students will cover tomorrow, but yeah, I would say this is going to be a more heavy mechanism-based midterm, and so we might want to say during our review tomorrow, bring up that point and then talk briefly about the big point in here, which is some math and some entropy discussion really quickly. So anyways, I'm going to leave that be again and get working on making sure we have a good class period tomorrow, and to get some discussions going with some students on what's happening in class, checking my email, and getting some discussion stuff. But I am a little bit tired, so I might take like a brief nappy break thing and then come back. But anyways, not the most helpful, I would guess, stream in some ways, but I do think it's important to at least add to this, right? This is pretty important for students to be able to see that there is this mechanism. Well, wait, not this one. This mechanism is the one that's not particularly talked about in class. It's almost assumed that you can do this, it seems like. Great. And I think we're mostly good, so let's say we're still prepping Tuesday class, and I need to see if that student has taken their midterm yet. I have not heard from them, which makes me a little bit nervous. Anyways, hasta luego. I will talk to you guys later. Did I ever go live? I'm sure I did. Anyways, okay, we're out.